Yes. Oh yeah. Do we have JavaScript? Good morning, everybody. We have two note takers, but no JavaScript. And Gori looks so happy. Was that a yes? Okay, that's a no. Any other volunteers for jabbering? Come on, somebody's got to be in Jabber anyway. You? Who's using Jabber? Nobody? But I mean, that's one. Come on, it's one of the easiest jobs. It really is. Okay, I'll hope that Gori gets it to work on his computer and just rely on him. Then, yes, I've been showing you the IETF IPR policy for a while without talking about it. So, there it is. I hope you read it. I'm not going to read it to you. It's always, it's been the same for a long time now. So, the agenda, a couple of talks. We should have ample time for them, but ask the presenters to keep to that time frame anyway, so we have enough time for discussion. And it starts with Carles. So yeah. It should be. What was the title? It's co-op thing, right? Yes.
Okay, good morning. My name is Carlos Gomez. I am one of the authors of this draft entitled Co-op Simple Congestion Control Advanced, also known as COCO. And in this presentation, I'll first give a motivation for this work, then I'll briefly introduce how COCO works, and I'll provide also an overview of performance evaluation results. Also, I'd like to say that some of the contents in this presentation have already been discussed at the Constrained RESTful Environments Working Group meetings, and the feedback collected has helped to shape both this mechanism and also the type of performance evaluation we are doing. Nevertheless, we felt somehow that it was necessary to present this kind of work here in this research group, so we believe your feedback would be very helpful in order to structure the way forward for this work. So, next please. Okay, first of all, a little bit of context. COCO is a mechanism intended for the Constrained Application Protocol, also known as COAP, which is a lightweight, efficient protocol for manipulating resources in constrained node networks. COAP runs over UDP by default, and COAP defines requests and responses which are sent by clients and servers, respectively, and then these are handled by a lower sublayer, which is this messages sublayer shown in the slide, which mainly includes some transport layer functionality. The messages can be sent as confirmable or con messages, which require the receiving destination endpoint to send an acknowledgement, whereas it's also possible to send messages as non-confirmable messages, non-messages, which don't trigger an acknowledgement from the receiving destination. Thank you. So the base COAP specification defines a basic, simple mechanism for congestion control for the transmission of confirmable messages, and the RTO for new confirmable messages is just chosen from a fixed interval randomly between 2 and 3 seconds. And the RTO, when the RTO expires, the new RTO value is calculated by applying a binary exponential backoff, and on the other hand, the number of outstanding interactions to a given destination is by default limited to 1. So COCO intends to be a simple mechanism for advanced congestion control, The key idea here would be to use RTT information in order to determine which is the RTO that has to be used in the transmission of these messages. Also, COCO defines a few rules for nonce, and as you can see, default CoAP does not take into account the network conditions in order to compute the RTO, and we try to take network conditions into account by using RTTs. Next, please. So let's see how COCO works. First of all, in COCO we make use of both strong and weak RTTs. Weak RTTs are round-trip times obtained when the sender has run into retransmissions, whereas strong RTTs are those in which the sender has been successful at the first transmission and we have got an acknowledgement from that. We believe it is necessary, as you can see later in the presentation, to consider weak RTT information because we are dealing with constrained node networks which are naturally lossy. So let's see how COCO computes the RTO. First of all, COCO runs two estimators in parallel, two RTO estimators in parallel, which are called the weak and the strong RTO estimators, which use the weak RTO estimator only uses weak RTTs as an input, and the strong RTO estimator only uses strong RTTs as an input. Both estimators use a scheme like the one defined in RFC 6298, with the exception that, as you can see in red, for the weak RTO estimator, the multiplicative constant for the RTT variance for the weak RTO estimator is substituted, so it's changed, instead of using 4, we use a value of 1. So when a weak RTT is obtained, the corresponding weak RTO estimator is updated, and then the same happens when a strong RTT is obtained, the strong RTO estimator is updated, and then there is an RTO overall, which will be used as the final RTO, which is evolved from the estimator that made the most recent contribution. Next, please. However, the contribution of each RTO estimator is not the same. When there is a weak RTO update, the contribution to the overall RTO is with a weight of 0.25, as you can see in the first formula here, and the weight of the RTO, the strong RTO estimator, is greater. It's a weight of 0.5. As you can see, the formula to compute the overall RTO is using an exponentially weighted moving average scheme. On the other hand, in order to further limit the impact of weak RTT information, only responses obtained before the third retransmission update the weak RTO estimator. So, as you can see, we are using weak RTT information, however, we are somehow limiting its impact, so we have to use it carefully. On the other hand, well, finally, this overall RTO value is dither between the computed value and 1.5 times that value in order to avoid synchronization effects happening in constrained node networks. Next, please. So another component in COCO is the use of a variable backup factor. The goals here would be, on one hand, to avoid too quick retries when the RTO expires and it has a low value. What we do is that if the RTO expires and it has a value lower than 1, then we apply a backup factor of 3. The purpose is to avoid retrying too quickly, which might contribute to congestion, whereas if the RTO expires and it has a value greater than 3 seconds, we apply a backup factor of 1.5, which is still greater than 1, and thus we still keep a safe algorithm. However, by doing this, we try to avoid unnecessarily long delays. And when the RTO expires and it has a somewhat medium value between 1 and 3 seconds, we apply the classic backup factor value of 2. Next, please. And the third component in COCO is an RTO aging mechanism. So when the RTO has a high value greater than 3 seconds and it has not been updated for a while, meaning more than 4 times the current RTO value, Then this formula here is applied in order to decay the RTO towards default values. And this is done because, of course, network conditions may change from time to time. And on the other hand, when the RTO has a low value, lower than 1 second, and has not been updated for 16 times its current value, then we duplicate the value of this RTO. So the idea is also to make the RTO value converge towards the default values. Next, please. Okay, so we have implemented Coco, we have running code. The latest draft version, Coco 02, has been implemented for Californium, which is Matthias Kovac's co-op implementation for unconstrained platforms. This implementation is publicly available. Here you may find the pointers to the relevant, available implementation. And also, Coco has been implemented for Erbium, which is the official co-op implementation for the ContikiOS, which is probably the reference operating system with support for IP-based protocols. And hopefully soon, this implementation will also be available. Next, please. So, we have been performing research work. We have been trying to evaluate the performance of Coco for quite some time. We have done simulation of 15.4 networks, considering various topologies such as grid topology, chain topology, dumbbell topology of various sizes. Also with different MAC layer settings, such as with or without MAC layer reliability, or the use of null RDC or ContikiMAC. On the other hand, we have performed experiments in real scenarios, and what I'm going to present next, in the next slides, is an overview of results obtained in these real scenarios. And of course, well, due to several limitations, it's not possible to give now all the details on the results and the work we have been doing so far. However, if anyone is interested, you may refer to papers which are already published or upcoming, hopefully. And you can also ask me or the other authors. So now let's focus a bit on these scenarios where we have performed the experiments that will be shown in the next slides. First of all, there is a GPRS scenario, which comprises a laptop which implements Californium, running a number of clients in parallel, which accesses to the internet through a GPRS link, and then at the other end of the path, there is a PC running Californium and running a server. And in the 15.4 scenario, what we have is also, on the left side, we have a laptop implementing Californium and running a number of clients in parallel. And each of these clients accesses a mode, so a node, in this testbed which is called FlogLab, which is remotely accessible. It is located in Zurich, in Switzerland. And each one of these modes runs the Erbium co-op implementation, and each client in the laptop on the left is accessing a server in a different mode on this FlogLab testbed. So, okay, the main purpose of this evaluation work is to try to compare the performance of Coco with that of default co-op. However, we have also considered other algorithms, such as Coco S, which is the strong-only version of Coco, which does not use weak RTT information. It only uses strong RTT data. Also, we have considered the use of a basic RTO scheme, which is a very simplistic but still RTT-sensitive mechanism, where the RTO is randomly chosen from the last RTT and 1.5 times the last RTT. And also, this basic RTO scheme is using weak RTTs. And also, we have considered the use of two additional RTO computing schemes, which have been designed for TCP. The first one is Linux RTO, which aims at reducing the contribution of variance to the RTO when the RTT decreases. And also it it avoids the problems of RFC 2988 RTO, which is sometimes getting too close to the RTT. So the aim is to avoid spurious timeouts. And on the other hand, the peak hopper RTO algorithm runs two estimators in parallel, the short and the long history estimators, and then applies the maximum of the two. This means that when there is an RTT peak, then the RTO is hot, and then there is a decay applied to the algorithm, but then the long history estimator dominates and also tries to avoid the RTO getting too close to the RTTs, and thus tries to avoid spurious timeouts. Next, please. So this is the first performance parameter we are focusing in, which is the ratio of successful exchanges per time unit that are achieved by the different algorithms in both the GPRS and the 15.4 scenarios. Here the experiments are as follows. The client sends a confirmable message, then this message, when it is acknowledged, the client sends immediately a new confirmable message so that we have some continuous traffic going on. So what we can see is that, well, the results are normalized to those of default co-op, and COCO is achieving the highest performance regarding this ratio of successful exchanges per time unit. We can see that COCO-S performs somewhat similarly, but not so well maybe. Well, I should explain before that we have done these experiments, as you can see, for different situations, which are the following. There is the use of 10 clients, then 20 clients, 30 clients, and 40 clients in parallel, so that we have an increasing degree of congestion and offered load to the network. And the column in white corresponds to the results in the Flock Lab, the 15.4 testbed. So the results for 10, 20, 30, and 40 clients are in the GPRS scenario, and the white ones are in the 15.4 scenario. Okay, so for a number of 10 clients, COCO-S doesn't perform really well. Later we'll see more details because it becomes too aggressive, because it doesn't include the weak RTT information component. And the basic RTO fails to perform well because it just uses the last RTT sample, and it incurs a lot of spurious timeouts. It retries too quickly. Then the Linux and Peak Hopper RTOs perform quite well, improving performance compared with the full co-op. However, not as well as COCO. We will later see a few specific issues that these algorithms have, but we could summarize that their behavior in this specific experiment is that Linux is a bit more aggressive than COCO, and Peak Hopper turns out to be a bit more conservative. Next, please. So, in order to illustrate what's going on, let's see these results, which show which is the average initial RTO computed by each algorithm, and this is in particular for the results in the GPRS scenario, with this varying number of clients in parallel of 10, 20, 30, and 40 clients. What we can see is that default co-op always leads to the same average initial RTO, because it just chooses randomly an RTO between 2 and 3 seconds. So this value here for default co-op is always 2.5 seconds. And what we can see is that when there is a low amount of congestion, meaning for 10 clients, all the RTT sensitive algorithms compute a lower average RTO. So in this case, default co-op is being conservative. However, what we can see is that as congestion grows, so we increase the number of clients, then the RTT grows, and all the RTT sensitive algorithms compute a greater RTO value, which is greater as the amount of offered load grows. And as you can see, already for 20 clients or more, default co-op turns out to be aggressive. So it is completely insensitive to what's going on in the network. So the other algorithms, the RTT sensitive ones, adapt their behavior. However, default co-op does not. Next, please. Okay, so this is another aspect from these same experiments, which is showing the retry ratio observed. So this is again the retry ratio normalized to the one of default CoAP. So what we can see here is that for a low amount of congestion, COCO more or less leads to a similar amount of retries. It's of course it's always difficult to avoid these spurious timeouts, especially when COCO is running an adaptive RTO scheme. You can see that the rest of algorithms are way more aggressive. For instance, in particular, COCO-S has a very high retry ratio because it's too aggressive for this low congestion scenario. So this is one reason why we should not consider that COCO-S is a good solution, a good alternative to default CoAP congestion control. On the other hand, the basic RTO mechanism is way too aggressive, and also Linux RTO is quite aggressive. Then when the number of clients grows and there is a higher amount of congestion in the network, as you can see, and also as we have seen in the previous slide, the RTT sensitive algorithms adapt their behavior and default CoAP becomes too aggressive. So this is why the retry ratio of the other algorithms compared with that of default CoAP improves significantly. Next, please. Other aspect we have analyzed in these experiments is fairness. So what we do here is that we evaluate fairness in the 15.4 scenario, which is challenging because there are different paths with different characteristics. In the GPRS scenario, the path is always the same for all communications between the two endpoints. However, here we have some short paths of just one hop and some longer paths of up to 4 hops in this 15.4 testnet. So we plot here the fairness according to RFC 5166 achieved by each algorithm in the experiments we were also mentioning before. And what we can see is that the basic Linux and PIC Hopper algorithms are quite less fair than default CoAP and also COCO. So what's happening? Well, these basic Linux and PIC Hopper algorithms, they are adaptive. They when they measure a short RTT, which is what happens in short paths of, for instance, just one hop, then they compute a low RTO, so they would retry quickly. And on the other hand, in the longer paths involving up to 4 hops, the RTT is greater, then these algorithms are leading to an RTO which is much greater, and then the long paths finally end up with less opportunities for transmitting, and there is a quite unfair behavior because these shorter paths take more fraction of the resources. So a further problem that is identified in Linux and PIC Hopper is that since they don't use the weak RTT information, then they sometimes reuse backed off RTO values, which could be avoided when sometimes there is weak RTT that could have been used. So why doesn't COCO suffer the same issue? Well, mainly there is this variable backup factor which somehow compensates the issues of fairness. In this case, when we have a short path of, for instance, just one hop, the variable backup factor tries to slow retries, whereas in longer paths, the variable backup factor tries to increase a bit to avoid the retries being too slow. So here we are compensating with the variable backup factor this natural issue of fairness. And as you can see, the fairness achieved by COCO is almost the same as that of default CoAP, which is completely neutral in terms of RTT and path conditions. Next, please. Okay, another performance parameter we have measured in a different experiment is the settling time. Settling time after a burst of messages appears in the network. Here, the idea is that the network starts from a low congestion scenario, low congested state, and then suddenly there is a burst of messages which have to be transmitted. For instance, this could be a group of sensors which detect some event. And then we measure the time it takes until the network has served 80% of the requests in a burst. So these are the results for the GPRS scenario, and as you can see, Cocoa provides the lowest settling time for 20 and 30 burst clients, whereas Cocoa S, which is a little bit more aggressive, performs the best in the lowest congested scenario. Also, as you can see, the Linux and Big Hopper RTO algorithms perform quite well in this scenario. However, if we look at the next slide, please. However, in the 15.4 scenario, as we can see here, the Linux and Big Hopper RTO algorithms clearly underperform default QAP. So this is a significant result, which means that probably we cannot recommend these two algorithms as possible alternatives to the default QAP congestion control mechanism. Which are the reasons for this behavior? Well, the reasons are the same that we have mentioned before, and the reason is issues related with fairness. And on the other hand, as you can see, in this scenario, Cocoa doesn't underperform and actually provides even a minor improvement compared with the settling time of default QAP. Next, please. So let's summarize a few observations from these experiments. We have seen that Cocoa performs similarly to or better than default QAP. It seems like Cocoa is making good use of RTT samples, and it is able to achieve a throughput increase and a settling time decrease without sacrificing fairness. So importantly, we haven't observed Cocoa to be underperforming default QAP in any scenario, so it might be a good candidate as an alternative to default QAP congestion control. On the other hand, Cocoa S seems to be a bit too aggressive, so this is maybe not so recommendable, especially in low congestion scenarios. Next, please. By the way, Cocoa S is a bit more aggressive because it doesn't have this weak RTT component. And on the other hand, we have seen that a too simplistic but still RTT sensitive mechanism may not be adequate because, as we have seen, the basic RTO scheme fails to perform well because it incurs a lot of spurious timeouts. On the other hand, we have analyzed these TCP-oriented RTO algorithms, and we have seen that whereas they perform well sometimes in some specific scenarios, they underperform in some other scenarios and in some performance parameters, and some of the issues are summarized here. As we have seen, there is a problem with not using weak RTT information, which leads to sometimes reusing backed off RTOs. Then the settling time is degraded due to issues with fairness, which is also degraded compared with default QAP. And also, these TCP-oriented algorithms don't use dithering, which is something useful in constrained node networks. So we could give an overall conclusion on these TCP-oriented designs by saying that they were not adapted, they were not designed for Internet of Things, IoT scenarios, and this is why they fail to capture all the peculiarities of these environments. Next, please. Okay, so the improvement achieved by Cocoa comes at the expense of some additional memory requirements. So here we can see the RAM requirements per client role with each of the considered algorithms. And here you can see that whereas default QAP just consumes 2 bytes of RAM per client, Cocoa requires 29 bytes per client. This is somewhat in the order of the RAM requirements of Linux RTO, and it is anyway below the RAM requirements of Big Hopper RTO algorithm. Next, please. Okay, so finally, I'd like to explain that in the IETF in Toronto, there was a good session in the Constrained RESTful Environments Working Group, in which we got a lot of feedback from many people, and then Carsten Bormann collected this feedback in the draft that you can see here, which tries to enumerate all the important questions and aspects that should be taken into account in the design or the selection of an advanced congestion control algorithm for co-op. So here I'll try to give a quick overview on whether we are doing well or not, taking into account this draft. So we believe the algorithm is for general use. It has been analyzed for a wide range of different scenarios and with different traffic patterns. We believe it protects the network, assuming as a reference the performance of default co-op, and also we believe this is regardless of lower layer mechanism settings. In this algorithm, we are trying to avoid synchronization effects by using dithering. It's true that we are missing one comment in the draft currently, which would be to mention which should be the granularity applied in the algorithm. We believe something like a 1 millisecond granularity would be okay, would be suitable. Also, we have partially considered the RTT history length that we should take into account in this whole set of experiments. And we believe we have taken into consideration the behavior of RFC 6298 and the modifications to this algorithm, for instance, as in the TCP-based algorithms like Linux and BigHopper RTO. Also, an important question is whether the algorithm is scalable, because we have tested or simulated COCO for networks of up to around 50 nodes. However, co-op networks may comprise hundreds or even thousands of nodes. And one important question is, okay, is this algorithm scalable regarding the number of nodes of the network? So we would welcome very much your feedback or even collaboration if anyone believes that there is an opportunity to do this kind of evaluation. Next, please. Then another important aspect is, okay, are we considering the whole range of parameter values in which the algorithm should operate? We believe we have done so more or less regarding RTT and also regarding the number of hops of an end-to-end path. However, we have possibly just analyzed low to medium offered loads, so it would be great to see what happens with really higher loads. And possibly the main missing technical component in the draft is some mechanism to control the aggregate behavior of a node, because a node may have exchanges in parallel with different destinations, and this has to be controlled in some way. Finally, well, we believe performance appears to be good, at least in comparison with default co-op. We believe COCO is self-fair, and also according to some results we have, it seems to be fair with TCP. And finally, something else that is needed is to analyze whether there are security considerations in addition to those of default co-op. So this is to be determined. Next, please. Okay, finally, a call to action. We would like to ask the research group to please implement this draft, and please tell us whether the specification is clear or not. Also, please experiment with this algorithm. So the point would be to try to find whether there are any performance issues, is there any improvement possibility, and also can we maybe cover the whole checklist we mentioned before. So in any case, we would welcome very much your feedback. So if you are interested in doing some research work or even in collaborating, we are of course happy to share the thoughts with you. So finally, well, here are the references to a couple of papers which are already published, and they are hopefully coming soon, at least one more paper coming soon, and another one maybe not so soon, but under review. And in any case, if you want to know about more details, you can refer to these papers or also contact me or the other authors. So this is all the presentation, so thank you.
Questions? Comments? Okay, that's my chance to ask one. I don't know very much about this whole congestion control mechanism, but does it maintain a window and send a number of packets per RTT?
Okay. No, actually, the base COAP specification defines a parameter which is called nstart, which would be the equivalent to this window, which by default is set to 1. So Cocoa doesn't disallow, let's say, doesn't forbid to use a greater nstart value. However, we got some feedback from the core working group by which it was possibly good to keep nstart to 1, and people were not really seeing use cases for an nstart greater.
Then my next question is, given that not very much harm comes from having a false RTO, I suppose, did you try to make it even more aggressive? Because I guess that the RTO in TCP is just has to be set to be very conservative, because you may retransmit the whole window, but this is a different thing here. So
yeah, the issue is that if we are too aggressive, then other performance parameters may be degraded. We have seen that Cocoa S, for instance, is more aggressive than Cocoa, and it doesn't perform always better, and sometimes it even underperforms. For instance, in low congestion scenarios, it seems to be retrying a lot. And this is an issue, considering that sometimes in constrained node networks, nodes are energy constrained, so we would be wasting a lot of energy.
Okay, thank you. Next.
Richard Scheffenegger, NetApp. So thank you very much for making all this investigation. So I believe much of this has actually come from my comments that I made in the core working group.
Yes, it is.
And basically, it's some of these, when I listened to your questions, came from the same background of TCP, and core is quite different beast. And I believe what we have seen now, this data really shows that this particular algorithm works much better for their environment. So thank you very much for this investigation.
Thank you.
Okay, I'll also say thank you and move on to the next speaker. Who, even when you're sitting, I think you should be in the pink box, because that's what it says. So we have to inform people. Yeah, put it in the pink box. Yeah. Oh, careful. Don't I have increase? Oh, I don't have your slides, right? You didn't have something. That's the thing. Right. So we need to log. Yes. Oh no. Is that you have a picture? You have it? Not going off. Oh. But I can press it for you. It doesn't matter. It's probably better. I think it's slow enough. It's not that long, is it?
He has to sit down. So.
Yeah, I think I can press for you.
Yeah, sure. Put it here.
Maybe it doesn't.
No, so we can press it. We can press for you.
Okay, if you want to.
If you want to.
It's just that for the. Yeah.
Yes.
That's why.
We can just.
We can press for you.
For you.
Don't worry about it. Careful.
Good morning. My name is Koen de Schepper. I'm going to present some work together with the people on the slides here. It's also partially funded by the RISE project, reducing internet transport latency. Go to the next slide. So the idea was to reduce the transport latency in the network, and the goal is to have a kind of unmanaged low-level service, low latency service. So universal support for low latency, and especially for adaptive interactive applications, it's important that you don't only have low latency for the interactivity, but it's also low latency when there is high throughput. So an adaptive application will challenge the throughput and will continuously be greedy if there is not enough throughput, so we also need low latency. Next slide. So today, the low latency is not so obvious because we need actually quite large queues to have the high throughput and the low drop probability. It results in poor latency, which is bad, of course. But on the other hand, if you reduce queues, the throughput will suffer and also the drop probability. So it's not really an issue of the AQMs in the network. They can control, they can limit the latency, but you still need quite some queuing. Now, the other side in the cloud, so typically applications today are especially interactive. They are nearby the end user. There is an access network next to it. So we have a data center nearby with low round trip time, let's say. But in the clouds, there are already solutions for better congestion controls. Like for instance, the data center TCP. They use ECN in a smarter way. So first of all, there is no drop, but they use it even better than ECN is used in normal TCP arena. They mark more often, and they mark faster, so very fast, so that they can achieve the small queues, and they can actually achieve both low latency and high throughput. So why not trying to use data center TCP completely to the end? It would be easy if we can replay the whole internet in one go and everybody uses data center TCP. That's of course not possible. Next slide. Although there is currently an implementation of data center TCP in Linux 3.18, it's a long-term support kernel. That's the one we use also. Also Windows Server has it. So in theory, clients could start using it, but the network doesn't support it, and so client still has to use normal arena, not to cause problems. Next slide. So what we want to, or what we tried, and the results we are going to show, it's ongoing research still. So we looked in trying to create a migration path for having data center TCP running next to normal Reno and Cubic by putting something in the network which makes them run fair. We at the moment looked only at the steady state throughput fairness. So no dynamic measurements have been done. We only measured steady state. We tried, of course, the system, and it works pretty good for low latency. That's what it's used for, but we didn't do any measurements yet. So I think I've said everything. Next slide. Maybe a short recap of what data center TCP does different than normal Reno. So data center TCP in the sender responds only slightly to congestion mark. So normal TCP Reno, once the round trip time is reversed, the congestion window is halved. Here it's only partially reduced, only when all the packets were marked, they also halve in one round trip time. The feedback needs to be adjusted, so we're not having the handshake anymore because it's not so important that we lose a congestion mark. We have to accurately feedback every mark and non-marked packets. And also the network needs to change so we don't smooth, no queuing delay, and we have a small thresholds in the network we immediately mark from the moment we see a little bit of congestion. The next slide. So what we tried on a real testbed, so with real service routers, real access nodes, real copper lines, real modems, real laptops. Okay, that's not so, and servers in a data center. The only thing we did, on one of the routers, where normally the traffic is shaped, we put a Linux box, we routed the traffic out, and we did here whatever we want to try. Okay, next slide. So we did first try, okay, let's see whether we can run data center TCP over longer round trip times. So we configured data center TCP with an instant queue size, so it's no smoothing, and we mark 100% after 5 packets in the queue. And we compared that to a Reno flow with a very tight red scheduler, but it could be anything else, which controls the queue to the minimum queue size which is required to have full throughput. We had in our test bed an 8 milliseconds unloaded round trip time. We throttled the user throughput downstream to 40 megabit. And we let run steady state run for a while and captured over 250 seconds. We plotted the queue size that we experience when we dequeue a packet, how many packets are still in the queue. So if you can see, if data center TCP runs alone, the queue size varies between 1 and 9 packets. Most of 40% of the packets is around these 4 or 5 packets. Reno, of course, because it has a big sawtooth, it's spread over. Data center TCP has a small variation, and also even with this big queue, there is still not 100% utility for Reno, because there are still moments when the queue size was 0. Next slide. So this is the same, but then the 250 seconds just plotted, just to give you an impression. So there is even on the second level quite some variation, and the peaks here that you see are actually at the back, so that's this underutilization. Next slide for data center TCP. It's really a smooth wall, it seems, over time. So it uses ECN, no retransmissions, and very small variation around this very sharp edge. Next slide. So the next thing to try is to run them together on a single queue and apply RED. And what did we expect? Data center TCP drives the queue size around this edge. Now it's smoothed, so it's probably a bit bigger, wobbling. But of course, 50%, more than 50% drop for the cubic or Reno flows. They reduce to window 1, having a big round trip time, so they're completely starved. And data center TCP evenly shares the bandwidth amongst all the other flows. Next slide. So, but we have no fairness, a high drop level for Reno, and continuous full queue, so that's not good. Next slide. If we did then the real experiments here, so we made all the combinations from 1 to 10 data center TCPs, from 0 to 10, to 0 to 10 Reno or cubic flows. I have to note that in our settings, cubic behaves as Reno, because the round trip time is very small. It falls back to Reno if the VDP is too small, so we didn't see any big difference. We tried both. So this is the throughput, and this is over 250 seconds. So it's samples of average throughput of every second in this case. So what you see is if Reno or cubic runs alone, it shares the bandwidth. There is a big variation, which is almost the same, no matter how many flows. Of course, we scaled the throughput. Here it's 40 megabits in the middle. Here it's 20 megabit in the middle. There it's 4 megabit in the middle. So the variation per flow stays the same, but absolute variation, of course, changes if you make the sum. Data center TCP. From the moment there is one flow, you see it hardly reduces, gets reduced, and Reno flows are really in the bottom. You see a faint red line. 2 data center TCP flows. They are pretty sharing, but very slowly converging because of the big queue. And you see it doesn't become better if we have more flows. It seems like there are more Reno flows, but actually it's because the scale is smaller. This is 10 times smaller the scale than this one. So we actually zoom in a little bit on the low Reno flows. Next slide. This is the queue size. So normally we have the scale is here 300 packets. So this is a PDF of the queue size again. With our red configuration, it's around 75 packets. No, I say between 30 and 50, between 50 and 100 packets. From the moment there is data center TCP, you see all the queue sizes shift to this maximum where the ECM curve gets high. Okay, next slide. So that doesn't work well. What do we have to do to make it work? There are two problems to solve. First is to try to identify which flows are which ones. And then obviously we need to align the drop and the marking probabilities in the correct way. We made a simple assumption, assuming TCP Reno today does not use ECN. It's practically not used in the internet. This data center TCP has to use ECN. So we just classify whether one of the bits is 1, then we assume it's data center TCP. If it's Reno, if both bits are 0, it's not ECN capable, we treat it as Reno traffic. So that's simple. The other thing is to align the marking probability in the next slide. Well known in literature is how the rates is related to both marking probability and round trip time. For Reno, for cubic it's a bit more complex, but this only gets into action when the round trip times are big. It's just to solve a problem because of this square root here in P that if the round trip time is very big, there is not enough feedback, so they changed it already. Data center TCP has here a square in the marking probability and a slightly different factor. And this is actually with this sharp edge. Now, we did some calculations because we were not so interested in that sharp edge. If you go to the next slide. If we have a more smoothed or a kind of red curve, whether it's offsetted, it doesn't matter. But if you have a certain stability point and a steady marking probability, well, actually, data center TCP behaves more with a P without a square. So it actually behaves like this. You can calculate that, and actually we saw it really with experimentation that it behaves like that. So what we assume now is are the two equations that we have to make work together. In the next slide, you see if we want to have the rates the same, and we assume the round trip times are the same because they share the same queue, we can simplify the equation and we get this simple equation that the marking probability must be divided by 1.63 and then squared to get the Reno drop probability. Slide. Fortunately, squaring a probability is very simple. You know, if you have a random, if you want to create a random variable, you calculate based on your queue size, queue time. You calculate a kind of value, probability value that scales within your random generator, and you compare if it's smaller than this. If your random value is smaller, you must mark or drop. Then you get B. Squaring means you just do it twice. If you throw a dice, you want 1 out of 6. That's simple. If you throw 2 dice, it's 1 out of 32. It's the square of the probabilities. So you only have to calculate this threshold once. You only have to generate 2 random variables, compare them twice. If they're both smaller, then you can drop in this case. So actually it's quite simple. Even you don't have to generate the two random variables. You can keep your previous one, take the maximum out of them, and you only have to compare once. So not so complicated. Of course, you need to have a probability value that you compare with the random variable in that case. Next slides. So we tried that. We built our coupled AQM, and we made a slope. We squared the slope, and we run data center, TCP, and Reno together. Based on the ECM classification, we applied this high marking probability for data center TCP, or this red light, you could say, the ECM Reno curve. So it looks a little bit like that, but it's not the same. It's important that if the marking probability or the throughput is here, that there is still a small marking, so it's not good that you approximate it, because otherwise if it's zero, Reno will push it here anyway, and you'll see there will be a big difference in marking probability for data center TCP. So if you apply this correctly, it works perfectly. Another remark is that the let's say, how do you say, the variation of the flow, of the queue size, must fit within this range. So if you go in and out, something else we detected, that means that you get, again, this on-off behavior, and that's, there is an extra square in this equation. So we have the forced power that we have to reduce, and it's variable depending on how much you go in and out, so it doesn't work. So if you can control your queue to a steady state marking probability, you have steady state fairness. We did it, we removed the offset because we don't want a fixed offset, and we made it like that. And actually, it doesn't matter whether a flow is using ECM or data center TCP in that case or not. They all, any combination of round trip time, they behave exactly the same as if they were the other flavor. So that's very good. We did that using simulation, but it's actually, in the next slide, works too good, because we have fairness for the throughput, but we have no latency gain. We made data center TCP have the same queue as Reno. You see? So to solve that, next slide, we have to use two queues. So we do ECM classification, again, Reno data center TCP, and if you have two queues, you can keep this one low latency. This can be the big queue which is required for Reno, and of course you need a scheduler. We want low latency, but the best way to schedule is priority scheduling. So we use priority scheduler here. We give strict priority to this queue. The only thing that we have to do is to couple, because now this is the only queue which is in the network, because if there is a queue, this one doesn't get scheduled. It grows very high, it will give a lot of marking, and this will be throttled and leaves scheduling opportunity for the second queue. So in this way, it's a stable mechanism which converges to the right equation. Now the only difficult factor was the 1.63 here. We incremented it by 5 because, well, we needed to increment that because now the round trip time is not fair anymore, because this one is 8 milliseconds in our setup. This one is bigger. How much bigger we can decide. So why not make our life easy? Multiply by 5. Become 8. 8 is a very simple calculation. We just shift 3 bits. And in the next slide, you see when we use that, this factor is 5. So we have to have a round trip time ratio of 1 out of 5. So we have to create an extra 32 millisecond queue in this case. If you divide by 16, you will have the 72 milliseconds. So depending on how much queue you want in your Reno flow, how far away traffic you want to support, you can configure that. So in this case, again, the ratio between the two should be stable again. Next slide. So we tried that as well. We made this, we have fairness again. Fairness again, it works very well. Next slide. What is also important is that we have no latency in this queue. This queue is always empty. The only thing is that we measure now this queue in time. That's important if you want to have a good fairness, because this is kind of automatic scheduler. It schedules with that, and everything it leaves is used here. So if there is fairness one-to-one, then this queue gets, if there is one flow here, one flow here, this queue is 50% of the time really empty, and this will be served by half of the bandwidth. Of course, if we measure here queue size, if there is 10-to-1, it will get only 9-to-1, let's say. It only can get 4 megabits here, so it's 5 times less throughput. So packets here have to wait 5 times longer. So if we correlate with size, the queue won't work very well. Of course, we can make this an adaptive thread to better control, or we can make it a cobble or a pi or whatever to control this queue to whatever we want. How we have made the coupling to the congestion control. Maybe next slide. Because here again we have 10 by 10 steady state throughputs for 250 milliseconds, and you see they work practically even. Reno gets a little bit advantage here and a little bit less here. That's because, if you go back to the previous slide, please. If there is a lot of flows running, the probabilities must be high, so the queue time also is a bit higher. If there is not so much, if there are only a few flows, the queue size will be less. That can be compensated by something which controls the queue time to a fixed value, like an adaptive thread or cobble or a pi, like I said before. Maybe the next slide shows the queuing. So here we see again the distribution of the queuing. That's Reno running alone on this red-like squared curve. And you see if there is only one flow, we have an optimal queue size. Of course, if there are more flows, the queue becomes bigger. But then data center TCP queue size are practically always empty. So there is no latency in the network. Only when data center TCP runs alone, I didn't mention that, but we have a backup, a fallback AQM when the queue is empty. I think it's in the next slide. No, not yet, but I'll show you in the next slide. So then data center TCP is controlled by its own sharp edge. Maybe another representation for the fairness compared in the next slide between the data center TCP, between the data center TCP and cubic running together. So from 1 to 10 again, from 1 to 10, we have the throughput ratio, cubic divided by data center TCP. So you see here is 1, it's a log scale. It's up to 40 times less throughput for data for cubic on a normal red AQM. We have coupled AQM with a dual queue. It's practically a plane around 1. A little bit more here to cubic when there are not so many flows, and a little bit less for cubic when there are lots of flows. In the next slides, you see the detail of the AQM. This is all what is in there. It looks complicated, but actually it are very simple operations in every box. We have here the sojourn time measured. So the first packet in the queue is used, and this is fed back compared to a random variable. Maybe I should mention we have 3 parameters: the Reno slope in the number of bits, a data center TCP slope in the number of bits, and a data center TCP threshold. This is what I said is a fallback AQM. So if this becomes 5 packets, there is always marking here. So if there is no traffic here, no feedback from this queue, then of course we also don't want to create a big queue here. Then If there is queuing here, is a queue time, we feed back, we shift that with a number of bits, which is 3 times bigger than we shift for Reno, so that's why you see there is a slower slope, here is a bigger slope. And we mark the packets that come here with that slope. And here it's just that we have the 2 random variables. We shift it with a lesser number, 3 bits less in this case, and we compare it with 2 random variables and we drop only when both are smaller. And the strict priority scheduler. So you see we have, again, fairness, very small queue, and we have queuing, which is needed for Reno. We have high throughput in every case. Next slide. So, okay, we did the experimentation based on steady state, but of course we wanted to try also some interactive applications. And it's really very nice to play with it. This is an interactive panoramic video application where on a tablet you can zoom in, zoom out, and drag on the playing field, the soccer match. So it's really like the image is sticking on your finger. If we run that with data center TCP, we go like that, and a bit later the image is moving. Also, when the congestion starts to grow, already when there is still enough bandwidth, this when we use normal TCP starts to become very shaky and not working well. With data center TCP, it's always low latency. The quality is adapted. We still have no queuing. In the network, we only control the queuing actually in the application because the application gets the queue then. Okay. Maybe some future work and conclusions. Preliminary conclusions, let's say. So we still have to do the dynamic behavior has to be investigated. Qualitatively, we saw a lot of improvement, so we want to quantify that and do some experiments based on that. So we have achieved, I could say, an unmanaged low-level network, so everybody can be fair, use the same throughput, have low latency, and we have native support for adaptive applications. We have a better use for ECN. We do more often marking. We can do more often marking than dropping. We also want to plead for this 1/T relation because it gives, first of all, faster feedback to the application. It's also scalable, more scalable. There have been scalable TCP and other work before that proved that. And we have additionally this simple squared relation between marking and drop, which can easily be implemented. And a very important aspect is, of course, the backwards compatibility. Whatever TCP flavor that we will use or want to use should respond to drop as Reno, because if there is no, there is only a drop tail, okay, we don't get any gain from latency, but at least we don't want to push away the normal Reno. So if there is drop, our congestion control should work like that. Currently, the 3.18 limits implementation does that not. So if there is a lot of drop, it's doing the same as if it were marked. So that's not good. That has to be fixed if you want to use this. Related to the steady state throughput fairness, there is also that it works only if data center TCP flows are terminated nearby. The round trip time is low because we balance the round trip time because it's 5 times shorter for data center TCP. We have to stop it 5 times more. So if there is an additional, let's say 100 milliseconds added to it, then we have 108 divided by 140, which is another ratio. So the data center throughput will be much lower than if we would use Reno. So possible solution is either the congestion controller could fall back to Reno or cubic if the throughput is too low, and the base round trip time is too long, or we define a TCP congestion controller which is less or even not dependent on the round trip time. Whether this will work, we still have to investigate as well. That's it. Next slide is questions.
Can you hear me?
Yep.
Is this mic working? Okay.
Yes, put your name, say your name.
Jana Iyengar.
Um, Thank you for this presentation. That's actually quite cool work. The question I have two questions for you. One, where did you get the 8 factor from in your loss rate derivation? And second, have you done experiments with mixed RTTs across flows? Because I don't know if I saw that, or maybe I missed it.
Okay. So the 8 factor. So originally the factor was 1.63, and that is if the round trip times are the same. So if they have the same queue, that's not a problem. We have to divide by 1.63. If the queues, if we have multiple queues, oops, I'm pressing the wrong button. Okay, here the throughput ratio. So it were the same two equations, but now just the ratio was taken from them. So 1.22 divided by the Reno and the round trip time of the Reno. Since we have here additional queuing, we need queuing for Reno, so we can give that, but that means that the round trip times are not the same. So this is a factor, in our case 1 to 5, so we have to compensate it to 1 to 5, so we need 5 times extra marking probability here. So we have to add this 5 here, and we just chose that factor, so it's very convenient to be 8. Is that clear? Is that?
And the 2 there is the 1.22 divided by 2. Where do you? Okay.
So what's it?
Okay. Well, so a subsequent thought is, if at higher RTTs, what you're observing is not Reno behavior but cubic behavior setting in, which means that you might need to change this constant here.
That the base round trip time is 8 milliseconds. So this only works if there is a fixed known round trip time to a local data center. That must be very clear, right? So that was also the last statement that I said. It depends a little bit on your base round trip time of your network. So it's not very automatically, but it's working. So you can achieve, say, okay, we give this service low latency, but of course if the latency is long anyway, it doesn't matter that much. You could as well use this, because then the queuing which is in your network is only in the same order as the round trip time, because it's dimensioned like that typically. You see? So it's only for low latency if you want to have really low latency. And then you have to take into account what is the ratio of the round trip times from the base round trip time, because you don't have any queuing here, to the queue that you want to configure here in your network, which is actually, for instance, set by CODL or by Pi or by adaptive thread. What is the target round trip time that we want to control here? See, and that's the ratio that you have to configure. And that's, of course, also the limitation of this. And that's why we say maybe it's better to use another congestion controller than data center TCP, which is independent from round trip time, and then we don't have this problem anymore. Okay? And the second question, I think you've asked as well, but I forgot.
My second question was if you did experiments with mixed round trip time flows.
Yeah, so we didn't do really experiments, but we made some calculations. So this is how if the base round trip time grows, you see if it shrinks, it's bad, because that's why it should be the lowest round trip time that you have, because otherwise data center TCP is very aggressive, and that goes very far. There's no limit to that. On the other hand, there is a maximum of 5 times less throughput for data center TCP if the round trip time grows very big. That's the factor. If the factor was 16 here, then it would be 10 times, maximum 10 times less throughput for data center TCP. Okay?
David Black, following up on Jonah's question. So I understand what you just said, that 8 is calculated off of a couple of fixed round-trip time assumptions. So if your assumptions change, the 8 changes.
Yes.
Have you thought at all about how to measure the inputs on the fly and adjust that on the fly, so we don't have a phone number that doesn't match what network's actually doing?
difficult, I think, to measure round trip times in the network. It could be done, and you can adapt that based on the per flow. That's really what you have to do in that case.
Okay, so something to think about, because if the assumptions are wrong, the 8 is wrong, and you obviously get different stuff. Comment, another question. Comment, first of all, thank you for the backwards compatibility discussion. I'm very pleased to see people thinking about how data center TCP can coexist in the network with our other TCPs. So in particular, the notion that, oops, if things get really bad and there's a drop, maybe you ought to treat the drop the way Reno treats a drop. Will probably keep us out of the soup. And a question: how are you classifying flows as Reno versus data center TCP? Because obviously you're effectively going through two, at least, virtual queues with two very different congestion controllers. Or sorry, not just two very different AQM algorithms.
So the question is how we...
That slide will do. There's an ECN classifier. What are you doing in that ECN classifier box?
We just check for the 2 ECN bits. If they're 0, 0, 0, we go here. All the other cases go here.
Okay, now what happens when Brian Trammell succeeds and we start turning on the ECN bits in Reno? What are you going to do?
We're going to put the ECN, the Reno ECN packets in here, and they're going to have bad luck.
Okay, like I said, what are you going to do?
We hope that we can use the ECN for this better.
My name's Stuart Cheshire from Apple. David actually just asked one of the questions I was going to ask. My observation when I'm looking at these graphs that you presented of what performs better and how the fairness works is there are 3 different variables that are being changed at once. There's what congestion control the end systems are using, what queuing discipline the network is doing, and whether ECN is being used or not. And when I see a graph that shows this performs better than that, is it that data center TCP is better than Reno? Is it that ECN is better than no ECN? Is it better? So it's hard to know what to make of the results when 3 variables are being changed at once. And I would also echo what David said, that we don't want to get in the state of assuming that only data center TCP is allowed to use ECN, because my laptop has been doing ECN for 10 years, and I'm not using data center TCP. And if Brian succeeds, we want to move more in this direction of all flows using ECN, and anything that penalizes those flows is the wrong incentive.
It's a choice I think we have to make and see whether we want to use ECN for a much bigger step or not. It's up to me to decide on that. I think it's a complete community that has to see this is an opportunity. Will we take this opportunity, or will we enable ECN for
I would argue that all traffic in the network ought to be ECN capable, because that's a better way of managing congestion than dropping packets.
Yes, that's true, but all can use another congestion controller, or we can use another way to classify, or there are many options. But at least I think it's important to know that with a simple squaring of probabilities and a simple scaling factor, it's possible to make different congestion controllers work together. I think that's the main thing. How this can be used, we assumed a simple assumption, ECN data center.
I'll make one more comment before I sit down, because we've got a line building up. I seem to get the sense from what you said that you were describing this queue management with a very sharp cliff as being in some sense an ideal, that 1 packet is okay and 2 packets is congestion. And the observation I would make in a very heterogeneous network is not all networks perform like a dedicated gigabit Ethernet link where the packets flow out at a nice regular rate. When packets are going over a Wi-Fi hop, multiple packets may be aggregated into one frame. There may be a moment of interference that causes a retransmission. So there is this short-term variability in rates. And Van Jacobsen makes this distinction in Coddle between what he calls good Q and bad Q. And good Q, that is like the internet shock absorber that absorbs that minor variation, is good as long as the Q drains back to zero. A standing Q is bad. So
completely agree with that. We only use this sharp edge here because it's simple, it's available, it's how data center TCP was. There it's only a fallback mechanism. So this can be anything. What we do here is not a sharp threshold as you see. It's a smooth curve. And I even didn't mention that it should be this red type Q. It can be adaptive, it can be coupled, it can be pi. Completely agree. This can be done with any congestion controller. And if you want to have this nice squaring of the probabilities here, your congestion controller should generate a p value that can be applied twice compared to the
Thank you.
Bob Briscoe taking a holiday from notes for a minute. Thank you, Caitlin, for letting me jump in because I wanted to respond to Stuart's point and David's. First of all, the use of ECN as an identifier for more than just ECN capability, we're essentially using it as a new service identifier on the basis that the last 15 years, 14 years or so of non-ECN deployment in the network. I gave a talk in TSB area last time, a couple of IETFs ago. We need, or network operators seem to need some greater incentive to deploy ECN capable routers than just no loss. And so we're thinking, right, let's make this an identifier of a new service for all traffic as low latency and low loss. And so we're sort of switching. We would require to standardize that at the IETF, that we are not going to get anywhere continuing to say, please can you turn on ECN, and they say why. And so we're saying this needs to be a much better service for it to be worth anyone going through the effort of turning it on. That's the basic premise that we started from.
It's definitely a simplification if we can only classify based on ECN bits, whether it's going to be possible or not. It's possible maybe also in a concealed environment.
And I've been having arguments with Koen as to whether we should have the step or whether we should have a ramp at that point. But we need to be clear that the good Q, bad Q arguments of Van Jacobsen are actually wrong when you think about ECN. Because with ECN, when you go over that ramp, you do not get a loss, you do not have to respond to that. You're an end system, you know what you've just done, you get a signal back and you can work with that signal. You've not got any losses, there's no impairment, so you don't have to respond to it immediately. You can smooth out that if you want to. If you're in the middle of slow start, you know that you've then gone over the point where you've got some capacity so you can drop out straight away. So it's not the same as with drop. Van Jacobsen's arguments only apply to drop.
Kalen Bessler in Accenture Systems. Your assumptions here seem to be based, you seem to be studying with specific topology. Have you done any evaluation about how these algorithms would hold up if you did something like move the clients to like VDI desktops that are also in the data center?
No, this is, yeah.
How would you tell the difference between the client that was in the data center and a client that was actually at home?
But in the data center, of course, you do just data center TCP. So internally in the data center, we don't want to change anything. It's only towards the clients that you could have, where you have the mix with Reno and data center TCP, that you would have to do this. You see? Because in the data center, you suppose either it's managed and everything is data center TCP, or if you want to support the mix, of course, you can also have some mechanisms like this.
Andrew McGregor. Firstly, I think I agree with what's been said already. A quick comment about data presentation. cumulative distribution functions are much easier to read than probability distribution functions. So, so I think this is a reason. This is at least a proof of concept of the idea that distinguishing between low rate and high rate ECN or drop based on ECN is worth doing. I mean, I see why to put a step function in your drop rate there. That's because that's what DCTCP was validated against, and so it's the right thing for DCTCP. Whether it's the right thing in general is another question entirely. Right.
Also, whether DCTCP should be used as the low latency congestion control is also not what we want to claim.
Question.
It's also not the perfect congestion control, so it also can be improved and so.
My comment is, my prime comment is, I think you must deal with the fact that the RTT can change. Because, for example, one of the DCTCP sources is likely to be a cache node that is in your, if you're an ISP, it's going to be a cache node that's in your own network. Now you do want to deal with the situation where the operator of that cache node wants to partially or totally drain it, and then a substantial fraction of the traffic is going to shift to a different RTT. You don't want that to kill you. Right.
Yeah, it's probably not killing because you have a ratio of 2.5 compared to another ring of flow to the same data set. So it's only an extra round trip time of 100 milliseconds more or less. So
I suggest you look at what happens when cache nodes get drained, because it's going to be bad and it needs to be sorted. Right.
Okay.
All right. Thank you very much. Yes, and that brings me to the next, who has been almost introduced already, Brian. And please try to stand in the pink box. Yes.
Nothing will fall from the ceiling.
Doing this very well already, I can tell.
From the floor.
Thanks.
Hi, so I'm Brian Trammell. I'll be talking about a paper we presented actually last week at PAM in Brooklyn, which is why I'm not as jet-lagged as I usually am at these things. As a joint work with Mina Kudavind, Dominic Bofart at ETH, Ian Lamont and Gary Fairhurst from Aberdeen, and Richard Scheffenegger, who there he is. He finally made it here. Thank you, Lufthansa. So next slide, please. So I probably don't need to show this slide to this room. This is the standard slide that I show undergrads and master students about what ECN is. Basically, yes, we defined it in 3168. We basically got a failed deployment of a protocol extension. There were rebooting routers, there were broken middle boxes. In the meantime, we over-provisioned.
Somebody remote says they can't hear you.
They can't hear me. So eat the microphone. Good. I haven't really had enough breakfast yet anyway. Microphone's pretty tasty. So yeah, we have largely a failed deployment. We've got rebooting routers, we had broken middle boxes. In the meantime, we over-provisioned everything. A lot of the problems that we were worried about 15 years ago seem to have gone away and now seem to have come back. And the argument is that this is relevant again. So one, there's the changing network environment. You have lots of new non-802-like non-802-like link layers that about which the assumptions about loss no longer hold. And you have changing requirements for ECN. So you'd like to be able to do things with DCTCP on the internet, for example. So in the meantime, when we talk about a failed deployment, you usually don't see hockey sticks on charts when you're talking about failed deployments. This is the proportion of ECN support in the Alexa top million web servers from 1999 to 2014. These data points here are sort of right after ECN. There was a little bit of a hiccup here where people actually turned it on and forgot to turn it back off. They turned it back off here. And then this point was a paper by Bauer at IMC. These were two in a paper that we did at PAM 2013. And this is our most recent paper. These were measurements that were done in September of 2014. And basically, this is what we're seeing here is the fact that Linux defaults to TCP ECN equals 2. So it'll do passive ECN negotiation. If you send it a SYN ECE CWR, it will send you back a SYNAC ECE, and it will start marking. Packets on both sides. If you ECT0 marking, not CE marking, unless there's a middle box in the way, which we'll talk about in a moment. So the server will negotiate ECN if asked, but no one is asking, right? So in the PAM 2013 paper, we basically did this active measurement to see how many servers would negotiate ECN with you, and it was about 30% of them. And then we saw what proportion of clients were actually negotiating ECN on flows on a national scale research network, and the number was tiny. It was tens of thousands out of hundreds of millions. So if we look at this graph, we see a success here. We've deployed ECN on the server side by changing the server-side defaults. Nobody's really made a choice here. As a matter of fact, if you look at the networks that are making choices, many of them are actually choosing to turn ECN off because it might be a risk and they see no benefit yet. But the defaults have made this curve happen. So the question is, can we leverage client-side defaults to drive deployment of ECN, and can we do it safely? So that's what we set out to answer in this work. So the methodology was we basically run N trials from N vantage points, and we do two connections very, very close to each other in time. We do a SYN ECE CWR followed by a SYN, I think, or a SYN followed by a SYN ECE CWR. I think it was the SYN first followed by the SYN ECE CWR. And we do this as close in time as possible from 3 different vantage points. We went out and rented 3 VMs from DigitalOcean.com. We did this because they have each of their data centers in their cloud is attached to the network by a different AS, so we're actually getting different routes. We have some path diversity, and they also all have native IPv6 connectivity, so we're able to measure and compare the situation in v4 and v6. And then we took a look at these the results that we got, and we classified them based on sort of which connections succeeded and which connections failed. For the most part, the connections always succeed regardless of whether you try to use ECN or not. Now here we're not looking at negotiation, we're just looking at connectivity failure. If I try to negotiate ECN with you, am I going to cause my connection to fail? A lot of them, and actually the second biggest class was they always fail regardless of ECN, so we just try to connect from a bunch of places, and it's broken all the time. It's remarkable how many servers in the Alexa top million over a week of trials will simply never respond to you. We did see in some cases it would always succeed without ECN or always fail with ECN, and this was classified as ECN-dependent connectivity. That's relatively close to the server. And then we get into the more interesting cases, which we'll see on the subsequent slides. So this is what endpoint-dependent connectivity dependency looks like. So we have multiple vantage points, and we have independent paths to the network until they join at how this machine is connected to the network, and there's either the host is breaking ECN or there's a firewall on path breaking ECN. So if this is the problem that we have, actually reading section 3.1 something something of RFC 3168 fixes the problem, right? So if you retransmit a SYN ECE CWR, you don't use the ECN flags, and you assume that it was the attempt to negotiate ECN that was the cause of the connectivity failure, and you fall back. So if there is something that's blocking connections that have those flags set, a retry will cause the connection to succeed.
Stuart Cheshire, did you mean the title to say endpoint dependent or endpoint independent?
This is endpoint dependent. So the connection is dependent on something that is associated with the endpoint, not something that's associated with the network.
Oh, endpoint meaning the server endpoint,
yeah, the server
client
endpoint,
end.
yeah,
Okay.
the far endpoint. So we see this on about 0.4%, 4 in 1,000 of the paths. And if you're using this fallback, that means you have a slight risk of increased connection latency. If you're not using the fallback, it means that you have a problem connecting. This reflects much less than 4 in 1,000 of the traffic. And in this case, we're thinking it's probably a firewall. See, the concept provider of the CDN can fix this problem just by changing the firewall configuration. This is probably even a firewall rule, as opposed to a firewall bug. This situation where you have path-dependent connectivity dependency is worse news. So here, we're able to connect from London using ECN. If we're trying to negotiate ECN, we don't have a connection problem. If we try to connect from Singapore, we do have a connection problem. This means that there's a device farther away from the server endpoint that's breaking connectivity. Fallback may not actually fix you here. We assume that if this box is breaking the TCP flag signaling for negotiation, it is more likely to break on other things. We definitely saw this in about 2.5 per 100,000, but these are relatively far down in the list of important things. Actually, a third of these were all GoDaddy parking sites. So they were different. There's one particular network that GoDaddy uses that on the path from Singapore, there's a box that breaks ECN, and on the other two paths, there's a box that doesn't break ECN. And I'm willing to take the risk of we break somebody's access to a GoDaddy parking site as a relatively low.
You need traceroute that does ECN markings.
Huh?
You need traceroute that does ECN markings.
We do need a traceroute that does ECN markings. We have one. It's called Tracebox. It'll only do the IP ECN markings because the assumption is that when you get a ICMP time exceeded packet, the ICMP time exceeded packet, if it has any part of the original packet, it only goes up to the TCP ports. And yeah, Richard is waving his hand. It's like, not always. In some cases, you get more data. But in many, many cases, you only get the ports. So you don't get the TCP flags, so you can't see what was modified with the TCP flags. And actually, in every single one of these cases, it's not just that Tracebox would have helped us, it's that the path is so screwed up that traceroute itself lies to us. Right? We tried to find, we said, okay, great, we have things that we can localize in the network. We have sort of a relatively weak tomography study. We can find these things. We started tracerouting them, and the traceroutes made no sense because there were things farther in front of the path that were breaking these things. We started doing some correlation of the routed prefixes and information out of the BGP looking glasses, and we did find that there is one particular ISP that I'm not going to name here that may be guilty of about half of this. But the reason I'm not going to name them is that we don't have enough information to say definitively, yes, this is actually a causal relationship. But yeah, we tried to use traceroute just lies to you in this situation. And here we come to the wall of numbers. So the connectivity dependency results, the important number to take away here is that in 99.5% of the cases, we can definitively say that if you turn on ECN to those endpoints, by default, you will have no connectivity problems, no connectivity latency problems. It just works. Then we get into sort of the corner cases. Down here we have stable ECN dependency near a host. This is a firewall rule or a broken firewall. Then stable ECN dependency on paths. This is 15. In 15 cases, we saw that there was definitely every single time we made a connection from multiple vantage points, it always failed at the same vantage points and always succeeded from the same vantage points. And there's also some what we call temporal ECN dependency, but we can't really rule that out as just things changed in the network in the time that we were running the trials. The total amount of time that we were running the trials encompassed about 11 days or 12 days, I believe. So there's enough down here in the underflow. There's enough just things are changing, or people are changing hosting providers, or people are turning things off and turning them back on that we can't rule these out as transients. But we can say that in 0.42% of the IPv4 cases and 0.09% of the IPv6 cases, there does appear to be something slightly more broken with ECN on the path where you do have to be. Next. This depends quite a lot on operating system and rank. So we use the old TTL trick, the initial TTL trick, to classify between Linux, Windows, and everything else / Google. And we see here that the things that don't have dependency are far more likely to be Linux than the things that do have dependency. Another interesting thing here is that the fact that the things that have ECN dependency in Linux seem to have a farther path from where we're doing the measurements than the things that are independent. There's a second little effect here. So this is looking at the probability of connection dependency on the rank of the site. And there's a spike here around the rank of 20,000. And we're not sure what that is. We do need to dig into that a little bit more, but it could be an effect of one particular CDN or one particular type of middle box that's targeted to sort of this market segment. Jana.
Quick clarification question. You're looking only at connectivity numbers, right? Not at CE marks or...
In this part of the talk, we're looking only at connectivity numbers. The CE marking and stuff comes later.
Gotcha. The TTL spectrum looks very, 64 and 128 are really large TTLs.
I'm sorry?
64 and 128 are really large TTLs. Is that...
a really large?
Really large TTL values, right?
So that's the remaining TTL. So this is
the remaining TTLs, of course.
Yeah, this is
yes.
This is basically classifying by the initial TTL, right? So 64 is the default initial TTL on Linux.
Okay, gotcha. I missed that.
So we're doing two things with this plot, right? We're showing one, the fact that the shape of the path length distribution is different between ECN dependency and independent, and also that Windows seems to have many more problems with ECN dependency than Linux. And whether this is a Windows hosting platforms tend to use middle boxes that are sold together, or whether we're actually looking at a lot of cases where it really is just a configuration or something broken on the host stack, that we can't say, right? Because if the dependency is on the common part of the path that we see from all three, and we don't have a trace route that's going to tell us anything about where that gets broken, then we can basically say we can't tell if it's the firewall or the last ALG or the last reverse proxy or the machine itself. And with respect to connectivity risk, it's not an important question, which is why we didn't dig into it. So next. So here we look at the negotiation results. This is the detailed data behind the plot that we had at the beginning of the talk. And here we see that we get 56% of IPv4 and 65% of IPv6 are capable of negotiating ECN. And almost all of these always negotiate. So every time that we go from every place, if it negotiates from one point, it will negotiate from all points. It will negotiate in one trial. It will negotiate in all trials. If we go down here to the ones that are not capable of negotiating ECN, there are a few that have a peculiar malfunction where they reflect the flags. So you send a SYN ECE CWR, and it sends back a SYN ACK ECE CWR, which could be a box, and it's either a broken ECN support in a TCP stack, or it's a middle box in the front that says, "Ooh, I see some flags that I don't understand, but I'm going to put them on the reverse flow anyway." So next slide. Once we get down into the signaling, we see there's that things are a bit less reliable, and the situation is a bit worse on IPv6 than IPv4. So here we have, the italic numbers are the ones that are the most important. The main ones to point out here is that we see almost every combination of ways that you can mess up the signaling. Bob actually had a look at this paper a little bit earlier and said, "I'm astonished that there are more than 16 ways to screw up signaling in a system that only has 4 bits," which I'm stealing, Bob. That goes into every future revision of this talk. This thing here, this is the largest number that is a little bit weird. This is where ECT0 gets set on the SYN ACK, which it turns out there's actually an RFC that says you can do that, which we didn't know when we first started doing this work. So we can see here that really sort of the relationship between the ECN, IP, and TCP flags, there are lots of little 1 in 100,000 or 1 in 10,000 signaling anomalies that if you turn things on by default, you're going to have to deal with, but these can be sort of classified and worked around. One thing that I think I got up to the mic and said at an ICCRG or a TSV area meeting a couple of years ago was that I was working very, very hard on finding a CE marking in the wild, and I am happy to report that we have seen 2. Both are from the same web server, www.grandlion.com. It's down in the 100,000s in the rankings. And the flow that we had was long enough that we never saw the CWR on the ECE that we sent back, but we cannot rule out legitimate CE marking in the internet. Congratulations, we have deployed ECN, we can all go home. Matt.
Yes, are you aware that there have been a small number of products out there, a small number of revs of a small number of products that were just putting garbage in those bits?
Yes.
Okay. Because they could masquerade as anything.
So we only saw things marked when we negotiated there. We didn't see markings on. So remember, we had 2 flows. We always had an ECN flow and a non-ECN flow. And the things that marked garbage much more consistently.
Hi, my name's Tim Shepard. Just a quick question. You said you've only seen 2 CEs, but I imagine in order to see, if you wanted to try and see congestion experience bits, you would have to generate some significant traffic. Were you just doing an HTTP
We were
get?
just doing an HTTP pull, so we were surprised to see it, or an HTTP get of slash.
Yeah, so
and it was like a 31 byte flow.
Yeah. So you would probably. I just want to suggest you might see more CE bits if you actually did significant uploads to the servers you were trying to do. And so you weren't really looking for that, right?
We weren't really looking for it. We just sort of found it. And the reason we weren't really looking for it is that it is, if you're just going to scan the top million and just get slash or head slash, nobody is going to notice what you're doing. If you're going to try and find a random page on that website that you can upload gigantic piles of garbage to, you're going to have to set up an abuse email, and you're going to have to answer it. And I know people who do, large-scale active measurements on that scale that have ended up having to get a separate AS from their home institution so that when people start null routing them, they don't break connectivity for the rest of the students, and I didn't want to go that far down the line. The next idea was to basically do all of this with, actually Richard did some initial work on doing all of this on port 25, which we got some interesting results from, but seems too dangerous to continue.
And I believe my home IP address is now listed somewhere. So
yes. Actually, while we're talking about brokenness, can we go back a few slides? One more. I wanted to point out the second largest percentage here on this slide when we're talking about what is the marginal risk of turning on ECN, and that's this number right here. This is of things in the Alexa top million list that gave back quad A records, 9.36% of them never connected from any vantage point. So 10% of the IPv6 web is just broken. And a lot of this brokenness is really interesting. You'd be amazed what you can see in the DNS. We saw something that came back as :1. We saw 40 or 50 FE80 addresses, and I've seen a couple of privacy extensions addresses, and lots of things where it's very clearly, we just plugged the thing in and the thing gave us an address and we didn't even think very hard about it. We threw it in the DNS, and it doesn't matter that it doesn't work because Happy Eyeballs works so well that no one's ever going to complain to us. I'm sorry, I'm supposed to be standing in the pink box, aren't I?
Stuart Cheshire again. Now, I have a tidbit, which I don't know what it means yet, but I'll share it with the room and other people can maybe look. I mentioned I've been running ECN for quite a while. If you look at the Wikipedia page for ECN, it tells you how to turn it on OS 10, what lines to put in the syscontrol.
And I'll note here that Wikipedia is the highest ranked website that will negotiate ECN with you. Nice and circular.
I donated some money to Wikipedia with a note thanking them for supporting ECN. For those of you running OS 10, if you do netstat-sp space TCP, it will give a bunch of stats. And on my machine right now, it says 12,558 connections negotiated ECN since my last reboot. 1,983 times CWR was sent in response to ECE. I have not looked to figure out whether this is happening at work or at home.
Can you send those flags
at
to the list?
Yeah, sure.
Yeah.
This might be a bug in the statistics in the kernel, which is why I say this is tentative right now.
Yes.
But there's certainly, I'm seeing a non-zero number, whatever that means.
Cool. All right, let's go back forward. Can we safely leverage client-side defaults to drive ECN deployment? I think we can say yes at this point. I mean, a lot of these numbers down here are in the underflow. What is the risk of connectivity to popular websites? It's order 10 to the negative fourth, so 1 in 10,000. On a path basis, when you're using fallback as an RFC 3168. So this is the SYN, the retransmitted SYN ECE CWR is retransmitted as a SYN. Fortunately, Apple and Microsoft do this already. We have a patch for the Linux kernel that we're trying to get into the Linux kernel, and we'll continue working on that. There was a little bit of a detour of how actually we wanted to handle ECN or ECN by default. Unfortunately, one of the Linux kernel developers whose job it is to look over the TCP stack is connected to one of the very few European residential ISPs that sets CE on every outgoing packet. So we found this in the earlier study, and I was talking to him about this, and he's like, yeah, but this is horribly broken. And I'm like, wait a minute, you're in Baden-Württemberg. Is your ISP? He said yes. It's like, oh, okay, bad luck. Which is illustrative of, I mean, it's, we are down in the underflow here. It's single providers, it's single configurations, it's single misconfigurations, it's single bugs that are the remaining problems here. Unfortunately, if it's the single bug that gets the guy who's going to put the code into the kernel that makes this by default, pisses him off to the point where he won't do it, then single bugs can still have quite an impact. So once we get the negotiation, the connectivity problems out of the way, we have about 2% of the cases in which signaling anomalies may interfere, in which you'll negotiate it and CE will be set on every packet, and you need to react to that in such a way that your congestion window doesn't slam down to 1 and stay there. So the next step to making the world safe for ECN is defining methods for detecting and reacting to these signaling failures. So this would be a revival of draft code of TCPM ECN fallback, which was originally looking at ECN fallback for this connectivity risk case, which it turns out is not that big a deal. It doesn't make much sense to go and re-engineer the stack above and beyond what 3168 already says for fallback. But it does make sense to re-engineer the stack to react to and shut down ECN in the case where it's obvious that you've got something on path that is messing with your signaling. So what to do next is define these signaling fallback methods. We're looking into measuring the situation for non-web services and access networks. So we did the Alexa top million because a lot of the other studies on ECN had done Alexa top million. We could actually do a longitudinal study. We could draw that line, and that line would make sense, right? But that's not terribly illustrative of where the problems in deploying ECN are. There's a lot of things that aren't the web. And there's a lot of things that aren't the web that need ECN more than the things that are the web do. So we're looking at measuring the situation for non-web services and access networks. We have a master student working on this right now who just 15 minutes ago showed me that he'd gotten the code running for the first time, so I'm optimistic about that. And then we want to take that and make that continuous measurement available at ecn.ethd.ch. So with that, other questions?
Richard Schaffenegger, one of the contributors for this measurement study. Do you want to go into the IT header bits bleaching and setting conundrum, or do we leave this out?
We'll leave that out.
Past the way when TCP is fixed.
Yeah, we'll leave that out past the way when TCP is fixed, because that's actually classifying that breaching and figuring out how that breaching is happening. So anomalous signaling is worse in that you're going to react to markings that aren't actually there. Bleaching, so dropping a packet that has CE marked on it is not really a problem, right? If I mark CE and then a later router drops it, great. It would have been dropped anyway. If an ECE ACK gets dropped, then you're also going to fall back on loss, just as if the fourth packet has been dropped. When you get into the weirder signaling, so some of the stuff that you saw, especially in the non-web case, then we need to. I've almost convinced myself that what needs to happen is we need to go back and draw a big nasty state machine and figure out how unnasty we can make that state machine in terms of figuring out a algorithm that is implementable and deployable for figuring out when to sort of gate and turn ECN off.
Good morning, Trevor Chandler. Can you go back to that slide that you were commenting about where you were receiving ::1 and FE80?
Yeah.
I'm not going to be able to sleep tonight if I don't get some discussion on that.
Which slide
anyway,
is that?
Go ahead.
Which slide is that?
Oh, it's this slide here. It's the
Is it that one?
9.36% of IPv6 is broken.
I'm sorry?
9.36% of the 100 or 17,029 IPv6 Alexa sites, you can simply never connect to them via IPv6. And we saw many misconfigurations in terms of people had just taken addresses that didn't make any sense and stuck them into the DNS for their, and said, yay, now I have IPv6 connectivity. So in some cases, they might not even be IPv6 connected. They just said, okay, well, I'm supposed to put a quad A address in here, and then I get IPv6 connectivity, because they don't understand that you actually need to have a route in order to get connectivity. Some of it may be, I mean, and this shows sort of the success of Happy Eyeballs, right? Because there's this much garbage in the DNS, and these are still in the top 1 million websites. So, the lesson here is if you engineer around a problem, the problem will stay.
Okay, thank you.
Yeah.
It's even more interesting when
this
you
would be
say...
a really interesting presentation to dig further in and then go give to the guys at 6man. But I'm guessing that the guys in 6man already know this and would throw me out for being a pessimist.
And you did say a moment ago that there were some situations where individuals did not even have IPv6 running. Did you say that a moment ago?
Yeah, I mean, like for most of these, we don't even have. So what we did is we took the domain list and then we just took these all and did a bulk resolution. And if there was a quad A record, we took it at its word, which was a mistake. We did do deduplication, so we only tried to measure localhost over IPv6 once. I didn't actually get a count of how many localhost IPv6 quad A records there were because of the deduplication stuff. But yeah, in many of these cases, the indication is there's a record in quad A that doesn't actually correspond to IPv6 connectivity.
Thank you.
You're welcome. And I'm sorry.
Okay. I guess we should head on to the next presentation. Okay, thank you very much. So that is Janje, if I pronounced that correctly. That? Where is the? Oh, it's on the stand. I think you don't have to worry about the pink box anymore, but because somebody has turned the camera. So, so now we're in.
Hi, this is Genji from Huawei. Our idea is increasing TCP's congestion window based on throughput. The motivation of our draft is extend TCP to support higher throughput and lower response time services such as 4K video. For the first item, maybe we needed to improve the congestion control algorithm. For example, like increase factor alpha and the decrease factor beta. And the second motivation is allow TCP to be configurable by applications. For example, application can customize TCP's congestion control algorithm and parameters according to his specific requirements. For this item, maybe we needed to extend the socket APIs. These extended APIs may allow applications to convey information. Okay, next. The background. Here the curves show the experimental results for the Reno and Cubic, and we ran these on the real network environment. From this figure, we can the network environment is target throughput is 50 Mbps and RTT is 60 ms. Then we calculate the target window size. It should be 2599 MSS. The initial window we used is 10 MSS. And in this experiment, we assume packet loss occurs when congestion window is equal to 130 MSS. And we can see that for TCP Reno, it may need 194 RTTs to reach to the target throughput. The target throughput is 50 Mbps. And then for Cubic, it needs about 229 RTTs to reach to the target throughput. And so we see from the results, we think that transmitting 4K video pose a great challenge to the current TCP. And next, please. Our message is propose increasing congestion window based on the throughput. The diagram shows the main steps for our proposed method. Step 1, the APP calculated the target throughput. Here we have assumption that APP can know the correct target throughput, and the network capacity can meet this target throughput. And also here we take the 4K VDR as an example. The target throughput may be larger. It has multiplication factors to the actual bit rates. And then the step 2, we need to extend the TCP socket options. For example, here we needed to add a new parameter, target throughput. This parameter will be transferred to the TCP protocol stack. And the third step, we calculate the increase factor alpha. Alpha is equal to target throughput multiply RTT and minus congestion window. Next, please. This diagram shows the increase factor for congestion window is calculated according to the RTTs. RTT is reflecting the network state, and then it had another imported from the application, the target throughput. Then we calculated the increase factor alpha. And the congestion window is adjusted for every RTT. Next, please. Here we show the window growth factor alpha. For example, when when the congestion window is equal to the target congestion window, and the alpha is 0 with the RTT equal to base RTT. And the general alpha curve is the one above the on the top. The alpha is equal to target throughput multiply ITT and minus congestion window. Here we defined a threshold T. T is defined to balance the congestion state of the network. For example, when RTT is longer, then the proposed method will not be used. It will fall back to the traditional TCP congestion control algorithm. For example, when the RTT is bigger than threshold T, maybe Reynolds or cubic will be used. So the T is the purpose of T is to make our proposed algorithm not too aggressive. So when the network is not good or congested. Okay, next please. Figure 5 shows the window curve with packet loss using the proposed method. Here we can see from the figure that only one RTT is needed to reach to the target throughput. And if there packet loss occurs between the second RTT and the third RTT, then it will also go back to the target throughput during less than one RTT. Okay, next please. Good. I think we missed 2 slides. I updated the slides.
Oh, I'm sorry. Okay. Thought I have to update it.
And then we also give the results for the we run in the real network. Maybe. Okay, here. This figure. This
Previous
figure.
or just this one? Huh?
Yeah, this one.
Okay.
This
Sorry.
one. Okay. This one we show the window curve with the packet loss using the proposed method. Maybe we cannot see it very clearly. The first beginning 30 MSS are used to estimate the base RTT, and then we can. And then there's a packet loss occurs, but soon it will go back, can come back to the target throughput, and you can see that the congestion window fluctuates a little, but it can be stabilized by the proposed method. Okay, next please. In this figure, there's no packet loss occurred during the in this figure, and we can see that also the beginning 30 ms are used to estimate the base RTT, and the congestion window can be balanced around the target congestion window, and also all these results are run in the real network, and we here show the main parameters for the network. Okay, next maybe we need to do more experiments, and maybe I know that it's quite premature to say that the second item, and here I present our method and solicit your comments. Here we have the issue to solve the 4K videos. Its characteristic for the 4K videos is higher throughput and lower response time. We propose our method, and maybe you have other ideas. Thank you, that's it.
Yeah, questions, comments? Yeah, should be okay, right?
I'd like the presenter to give us a view of... okay, Marie-Josée Montpetit, actually MIT. I would like the presenter to give us some details on why is this working and why this will not lead to congestion collapse in the internet.
You mean the background why we need propose this kind of message? I mean, I think I just message in the draft we show the issues about transmitting the 4K videos because in the current real network cannot using the traditional TCP it cannot meet the requirements for transmitting 4K video. That's why we proposed the method here, and then for not to make the network collapse.
Okay, I made my whole career transmitting video over the internet, so I will tell you that there are ways of transmitting high-speed video over the internet, but without killing the internet. So I'm not convinced that what you're presenting, actually by basically hard coding things based on throughput. Throughput is based on the congestion window. Don't transmit over TCP. Do something else. But this for me, I'm sorry, I feel strongly about this because I think this is not a valid solution for transmitting 4K video over the internet. I'm sorry. And if anybody disagrees with me, I'm open to discussion.
But Briscoe, can I try and maybe explain why Marie-Josée might be saying this? You seem to be trying to get to 4K within a round trip time. Is it? Yeah? Or get to the target rate within a round trip time. And the point of TCP is you don't know what the rate the network can sustain is because you don't know what other flows are there. There may be other flows that arrive and depart all the time, so you don't know what's there. Therefore, aiming to get to a rate after a round trip time, which means you've had no time for any feedback, is completely going to break any other flows that are there before you can respond. I think that's what
Just a quick thing. The time is getting short, so I have to cut the line. And if your comment is going to just repeat, basically that this is not going to work, like we've heard people say, then maybe save time. Okay, Stuart is next.
My name's Stuart Cheshire. Thank you for coming to IETF and giving this presentation. For use on the general internet where you don't know the capacity, this is dangerous. For use in your data center where you're delivering video to clients and you absolutely know you have excess capacity, you can just set the TCP initial window to 400 packets and then you will dump data into the network at the rate you want and it will work absolutely perfectly up until the point where it completely breaks. And as long as you engineer it so that you never hit the point it breaks, that's fine. My comment about the presentation is you started off with a model of when a packet loss happens halfway through the slow start phase. And it's well known that that is a vulnerability of TCP, that if you have a packet loss, it then goes linear and can take a time to reach the right rate. By the end of the presentation, you're showing models where no packet loss occurs. And showing that the new system works when there's no packet loss to address a problem with Reno when there is packet loss. Sorry, I said that wrong, but it's not a like comparison. If there's no packet loss, slow start works fine. And if there is packet loss, you should be using packet loss throughout the analysis rather than just assuming no packet loss at the end.
John
Chen. Can you go back to your slide 2?
To which one?
Slide 2. The one that he presented, Reno and Cubic, is really bad. Yeah. So your target CUN is 259 packets. And if you use slow start, that takes only 5 round trips. And as far as I know, Reno and Cubic both use slow start. I mean, Cubic use a slightly different called high start, but basically it still doubles a window. So how come you are seeing like it takes 1.7 seconds for Cubic or 11 seconds for Reno to reach that throughput?
I can answer that question. It takes that because it's assuming a packet loss happens at an inopportune time. So this is not saying it always takes 11 seconds. It's saying that very, very rarely when a packet loss happens at the wrong time, it could take 11 seconds.
I see. So I guess I misinterpreted the result. I guess, yeah, okay.
Okay, keep it short, please.
Yeah, my name is Joseph Karajanis from Huawei. What I would like to mention is that 4K video, and in particular ultra high definition video, is an application that will be deployed, I think, massively, and we could use TCP for that in some cases. So there are situations, deployment cases that this is required. So the question is, can we use the current congestion control algorithms that are provided by TCP at the moment to support that? So the question is that. So how could we support ultra high definition video assuming that the transfer protocol is TCP? So then the research that could be done.
The line is cut. Sorry, we really have to end this.
So that is the question.
Also, Matt, sorry, we have.
I know that we have done a lot of experiments of this, and we can prove. I mean, this is just a subset of the experiments that we show here. We don't have time to present all the experiments, but I think that by showing and by doing maybe more experiments, we can also provide more. Say we could justify what we are trying to do here.
Okay, Mira.
Mia Kulevin, very quick. Can you go on the next slide? So I think the main problem here is this red text that says the assumption is the network capacity can take the target rate. That's just not true. You should never make this assumption, and that's why we have congestion control. That's the main point.
Okay. We have to go to the next presentation. So thank you. Right, okay.
Hello everyone, my name is Jim, and today my topic is combining TCP with coding in wireless networks. Yes, please. So first is a problem statement. As we all know that the TCP was primarily designed for the wireless network in low bit error rate, where packet loss caused by network control. So in wireless networks, a lot of factors lead to unstable air link, which causes high bit error rate, and there's high packet rate, packet loss. So traditional TCP mistakes the link error packet loss as a congested packet loss, and therefore reduces the sending rate unnecessarily in wireless network. Next, please. We have done some tests in our network, including Wi-Fi and LTE. Here are some test results. And from the results, we can see that in many public Wi-Fis, we indeed encounter some packet losses. Where in the LTE, when the signal is good, we can see that the packet loss is low. And where in some cases, such as urban obstacles, the packet loss increases. So next, please. So we consider to use coding to TCP to improve its throughput in wireless in order to erase packet loss. And this is just an example of the coding. So in the user layer, we have a packet 1 and packet 2 send. And in the coded layer, we combine the two packets by using coding algorithms. One of the algorithms we use here is the network coding. And then we generated 3 codings by 3 coded packets by involve redundancy. And then send all these coded packets to the standard TCP stack to send. And during the transmission, for example, one of the packet is lost, and the other 2 have arrived successfully at the receiver side. The receiver side detects that it can decode the TCP the original packet successfully, and then it acknowledges to the TCP standard that it received all the 3 packets successfully, and then the TCP standard will still going on to send subsequent packets without retransmission, timeout, and in this case, the TCP throughput can be improved. Next, please. We can also use...
Can we take a question here? Okay, so you're saying not a retransmission timeout, but are you saying you still do a congestion control response to that packet loss?
Okay, in this case, because the packet loss is recovered by the coding, so it's not sensitive to the congestion. Yes.
So I say this is not TCP.
Yeah, just go on.
We also use the systematic coders, and in this case, the original packets and the coded packets are sent simultaneously. This case is similar to the previous one. Okay, next please. So we introduce the coded TCP architecture of the sender side, and from the user, the user data is sent from the application layer to the encoding buffer, and the encoding buffer consists of coding blocks. The coding blocks contain the same number of the coded of the original packets, and in this example, the number of the original packet is n. It's assumed to be n, and then we encode the packets in each coding block, and the output of the number of output coded packets is m. We make sure that m is greater than n in order to ensure the redundancy is involved and the coding is going on. In this case, we make sure that the coding algorithm make sure that if any n of m packets is received at the receiver side, it can successfully decode the packets. So next, please. In order to decode the coded packets in coded TCP, we also involve the coding headers, includes the block sequences, original and coded numbers, and the coding coefficients. The coding coefficients indicates the coefficients of original packets involved in combination. The coding coefficients are generated by coding algorithm and used by receiver to decode. Next, please. And this is the process of the receiver side. The receiver side records the number of the received coded packets, and in each block, when packet arrives, the receiver side in each block checks whether it is the number of the received coded packets is less than the number of the original packets. If yes, it executes that the packet received successfully. This is just the same as the standard TCP. And if no, the SDK is that all packets in the coding block received successfully. In this case, it no need to wait receive to other packets in each coding block, and it can decode the packet successfully. Okay, next please. This slide discusses the interworking with the standard TCP. So the coded TCP transmits the coded packets and cannot interwork with standard TCP. So in order to invoke coded TCP, should be able to choose whether or not to enable coding dynamically. If coding is disabled, coding TCP behaves as the standard TCP. This shows we can define the 1 bit in the result field of the TCP header to identify whether transport uses the coded TCP or standard TCP. The below shows 2 examples, and the example at the left side is in the case that both sender and receiver uses the coded TCPs. So after negotiate, they communication by coded TCP, and on the other.
Are you gonna take a question now, or is it okay? There was a question. Yes, Brian,
Hi,
please.
which bit do you want?
Sorry?
You need a bit. Which one do you want?
Oh, at this case, I just use one of the result field, and I also use the TCP options. We cannot make the final decisions, and in our experiment implementation, I just use one of them.
The reason I asked the question is that the answer to that question will completely determine the deployability of your proposal.
Okay, okay.
It will, so depending on how you want to do that, it'll be either difficult to deploy or impossible. So more specifically, well, I'm a little more optimistic than Bob is.
So
Smidge. No, so more to the point, this is a really interesting method for doing error correction. Why are you trying to wedge it into TCP? Right, you could take this on top of any datagram transport, put a little bit more work into adding the bits of the retransmission you need to make it work, and you get something that might deploy.
Okay,
So come to the Spud BOF at Wednesday morning at 9 a.m.
Okay.
Thank you.
Okay.
Stuart Cheshire again. This network coding approach may be appropriate at the Wi-Fi layer. You presented an earlier slide where you said you measured 1% packet loss, and then assumed that was random cosmic rays. Maybe the 1% packet loss was in fact congestion, and the correct behavior is in fact to slow down when there are more people trying to use the wireless network. If we all respond by saying, hey, there's packet loss, let's send twice as much traffic, that may make the problem worse instead of better. So in the initial figures you presented, where you said there's 1% packet loss, you're assuming that was sort of some weird, mysterious Wi-Fi failure, and maybe it wasn't. Maybe that was exactly what we think it is, which is congestion. If Wi-Fi is unreliable, then that's a job for the Wi-Fi Alliance or IEEE to fix, and this technique might be something to present there for how they can make that one Wi-Fi hop more reliable. But doing this end-to-end over 30 hops is not the appropriate application of the technology, because the individual links that make up the internet have to be largely reliable. They don't have to be 9 nines reliable, only losing one packet in a billion, but they do have to be at least 99.9% reliable in order to get a reasonable end-to-end transmission. And the reason I'll say that is, imagine we took network coding to its logical extreme, where you just spew an unconstrained flood of data into the network and rely on reconstruction at the other end. Well, if the first hop has 50% packet loss, and the second has 50, and the third has 50, after 10 hops, only one packet in 1,000 that you inject into the network is getting it out the other side. And my phone is burning an awful lot of battery power, sending an awful lot of packets into the network, when only 1 in 1,000 or 1 in 10,000 actually makes it to the other end. And that's an awful lot of radio spectrum being wasted with packets that never make it to their destination. You can't build an end-to-end network with massive rampant packet loss, which is why I think Miria said you have to slow down when there's congestion. This is a reasonable link layer technique. It's not a reasonable end-to-end technique.
Okay, thank you.
I will ask the next comments to be super short, so you can show maybe 2 more slides or something, because otherwise, I mean, we're almost at the end. No,
Google.
we only have 2 more. No, sorry, I can't. Because otherwise, it's going to be impossible to. I mean, we just have to terminate the presentation here. It's the end of it, right? So that's why. So you two, okay. Keep it short.
I'd like to disagree slightly with Stuart, but not totally. So, having had a bit to do with Wi-Fi rate control in the past, only 1% packet loss on Wi-Fi? Really? That's a really good Wi-Fi link. So, you know, it is appropriate end-to-end in some situations, because you get situations like Wi-Fi where the inherent packet loss underlying the link layer's already existing retransmission mechanism is something like 45%. All right. Or you're wanting to run as a best effort scavenger service in a diff-serve network where the lowest effort class is getting fairly high packet loss.
Really important.
So that's kind of a reason to do this end-to-end. However, as has been said before, trying to munge it into TCP, that's probably not going to fly, because TCP is already pushed for extensibility, and trying to find code points and options to do this we've effectively run out. Doing it as something like Quick, or any number of other datagram-based transports, perfectly fair enough to try. You still need congestion control of some sort. However, you can't just say, oh, well, we recovered from that, so it's okay to continue sending at the same rate. But
No, but I
taking
did.
that as equivalent to a high rate ECN mark, that would be fine.
Yeah.
You've got to do
I did
something.
ask you to keep it short. Next, and then.
David Blackman, I will keep it short. Stuart said almost everything I got up here to say. This proposal is fatally flawed because it ignores congestion. You are going to break the internet with this. Stop it. You need to do what Stuart said. You need a reliable way to figure out that the link did in fact drop the packet because of link errors and that you're not dealing with a drop that is trying to signal congestion. The drop signals congestion, you must react to it.
Okay, I'm afraid I cannot allow you to continue that presentation because we gave you only 10 minutes and there were comments already and we had to, I mean, we were at the end of it. It's 11:30. So if you have any concluding words or one slide you want to show to terminate.
Okay, so maybe we get to the latest.
Yeah, so the results. And
Yes. Okay, so we also analyze the relation with the TCP conjunction. As you say, yes, in these current implementations, it indeed impact the TCP congestion control, and we realize it and we understand it. So we can say, in our test, in our implementation, we set the maximum coding radius and as a high threshold, and we analyze it into 3 cases. And in the 3rd case, it indeed, if the packet loss can be recovered by the network by the coding, the TCP throughput indeed the TCP conjunction indeed disobeyed. So we admit it, and maybe we can do more research in the future. We know it. Yeah.
Okay, so I think we can use this as last words and end it here. Thank you all. Thank you for attending. Thanks to the speakers. Thanks for returning the blue sheets, and have a good lunch.
Yeah, the deep dive is yours, right? Oh, it was already. It was already there. It was already there. Oh, okay.
I thought it was.
Was it?
Mit der Klassifikation, das ist
Eure Veranstaltung.